So today's topic, I've titled it Radioactive Decay, but it's really a whole bunch of things shoved together. I want to basically begin with some historical context again. We've been discussing for the last few days the idea that around the turn of the 20th century, science in general really had a fundamental change. Physics was kind of at the forefront of it, with the idea of discovering, well, what is stuff really made of, right? But before we got to basically J.J. Thomson, in I think the year about 1890, give or take, 1893, somewhere around there. Basically, the model of an atom was that it was an indivisible sphere. That was basically John Dalton's model. And then all of a sudden, a whole bunch of scientists in rapid succession, I mean, rapid meaning like within like 10, 20, 30 years of each other, they all of a sudden discovered new pieces. Thomson discovers subatomic particles. He realizes that no, the atom is not as small as it gets, you can have electrons. Then Rutherford comes along, a decade or so later after that, discovers there's a nucleus out there. And then Bohr comes around a few years after that and says, not only is there a nucleus, but we think these energies, these electrons exist in energy levels, and they really can't be in between there. Okay? And that's the context I want to begin this lesson, which basically starts here, is that in the early part of the 20th century, there was a lot of advance in physics. But chemistry went hand in hand with it. And I know I'm not your chem teacher, but we need to know some of the basics of chemistry. Basically, what ended up happening is before Rutherford's time, scientists didn't really fully know what was going on in terms of the periodic table. They knew that there were different atoms, right? They knew about hydrogen and chlorine and phosphorus. They knew all those things were different, but they didn't necessarily know why. What differs? For those of you guys who know chemistry, what makes hydrogen different than helium? What is the fundamental difference between everything on the periodic table? The number of But if scientists didn't know that protons even existed until around the time of Rutherford, when they discovered the nucleus and realized, oh, hey, there's electrons and positives, right? Until they figured that out, chemistry was really painting a really incomplete picture. And we don't necessarily talk about that as much in our chemistry classes because we don't do a lot of historical context there. But hopefully that makes logical sense, is that before this time, atomic models were incomplete. Scientists did not know about protons, neutrons, and electrons. They weren't discovered. So they had a periodic table, but they didn't really get why the periodic table worked yet. So my beginning lesson then is we need to begin, and you guys need to know a little bit of periodic table work in order to be able to do some of the physics stuff we do in a bit. Does that make sense where we're going? So my first slides are basically all about these terms here. And these are words that over the next few slides I'm going to discuss with you. And like I said to begin class, I'm sorry if this is boring and you're like, Chris, I took chemistry. I get this stuff. Sorry, I just want to make sure we've covered the bases. Okay. So here are some terms I need you guys to know. The periodic table in chemistry, which I've handed out to most of you guys. Do you guys need one? Here's a periodic table. The periodic table in chemistry is organized by protons. That's how we differentiate matter. So what is the fundamental difference between hydrogen over here, number 1, and helium, number 2? Number of protons. Hydrogen has 1 proton, helium has 2 protons. Lithium has 3, beryllium has 4, all the way up to lead having 82, and all of these weird guys here, right? That is literally how the periodic table works, number of protons. So the word that we use to describe that is called atomic number. And those are the numbers on the periodic table. It tells you how many protons there are. So if you weren't aware of that, in this term right here, the atomic number, if you want to write it out, I guess, the atomic number is the number of protons that an atom has. I have a really stupid way I teach my grade 9s and 10s this, but maybe it'll work for you guys too. It's a dumb analogy. You guys ever watch the TV show The Smurfs? You ever see that? The little blue Smurf guys? There's Grumpy Smurf and Clumsy Smurf. You guys clearly don't have 6-year-olds. My daughters love the Smurfs. Okay. You guys, no one's seen the Smurfs? Seriously, nobody's seen the Smurfs? Well, this analogy doesn't work. If you've seen the Smurfs, basically the Smurfs are all named based on their personalities. So Grumpy Smurf is called Grumpy because he's grumpy, and Clumsy Smurf is called Clumsy because he's clumsy. Anyways, the dumb analogy I have here is that all of the matter that we know of, hydrogen and helium and lithium, yes, we gave them names. And often those names are based on scientists who discovered them, or maybe they're based on some sort of Latin word. But ultimately, their characteristics are what define them, in the same way that the Smurfs are defined by their names. What is the one defining characteristic, girls, please? What is the one defining characteristic of hydrogen? that it has one proton. That is its most important characteristic, and therefore that is how we identify it. Grumpy Smurf then is identified based on his grumpiness. That's its identifying factor. Yeah. Sure. Yeah, same concept. Okay, so if you haven't seen the Smurfs, let's go with the dwarfs, right? Why do we call him happy? Because he's happy. It's a dumb analogy. Let's move on. Long story short, atomic number then is how many protons you have. However, scientists discovered that there was more than just protons out there. They discovered the subatomic particles, right? Protons, neutrons, and electrons. And once Rutherford realized that there was a nucleus, he realized that in the nucleus there was, where's a good picture here? I'll go with this one. I'm going out of order here. In the nucleus, there were both protons and neutrons in nuclei. And so that leads to the concept mass number. And hopefully you've seen this in chemistry before. If I gave you a notation like this, C612. Anybody ever seen that in part of a chemistry career before? Grade 10 or grade 11? The 6 right here is the atomic number. It is what defines carbon as carbon. It is defined by its 6 protons. But this 12 is the number of, we would call them nucleons. Nucleons. And your nucleons are basically your protons mixed with your neutrons. Scientists didn't know about protons and neutrons until about the turn of the 20th century, right? So this number right here then tells you how many total things are in the nucleus. But wait, 6 of them are protons. So if you guys have seen this before, if you want to figure out how many neutrons there are, you subtract these numbers. If you take 12 minus 6, that tells you your neutrons. Is that familiar to some of you? I'm boring you? Yeah, I'm boring you. So let me give you one more random one here. If I were to give you like unknown element question mark, and I were to tell you that this was an 11 and this was a 5, could you do 2 things for me? Could you first tell me who the unknown question mark is? And then after that, can you tell me how many neutrons there are? So first let's try unknown question mark. How do I tell who this element is? I look at the number down in the bottom corner called the atomic number. Number 5 on your periodic table is boron. So that is the key defining characteristic that identifies it. They are identified by their protons. This is no longer question mark, it's now B for boron. Boron has to have 5 protons. Here's the thing about neutrons though. There is no number of neutrons that you can have. You can have 5 neutrons, or 6, or 7, or 8, or 23. And so because neutrons are neutral and you can have a different number of them, you always need to know what's called a mass number. And the mass number is basically adding the protons to the neutrons. So this particular boron has 6 neutrons. This one boron atom has 6 neutrons. 5 and 6 adds us to 11. Now, is it possible to have a different, we call it an isotope? Sure. Here's another slide I want to go to. These are known as isotopes of each other. These are 3 different carbon atoms, and they're all considered carbon because they have 6 protons. That is their key defining characteristic. This carbon right here, though, has 6 neutrons. This carbon right here has 7 neutrons, and this carbon right here has 8 neutrons. How in the world did I do that? Well, I subtracted. 12 minus 6 means there's 6 remaining neutrons. 13 minus 6 means there's 7 remaining neutrons, and 14 minus 6 means there's 8 remaining neutrons. Okay. Those are called isotopes of each other, and what it refers to is the fact that they're all still carbon, but they're slightly different from each other based on their mass. Okay. Now, when I'm originally teaching kids in grade 9 and grade 10 about mass number, they often get it confused with what's known as the molar mass, which for carbon is 12.01. And any of you who have done chemistry at some point before, you probably know a few of these, just like off the top of your head. Like hydrogen has a molar mass of 1.01. Nitrogen is 14.01. Sodium is 22.99. You guys familiar with some of those numbers? Those then are the average of all of the different possible isotopes out there. One individual atom is either a 12 or a 13 or a 14. One individual atom. But like, when do we work with one atom? Right? Usually we work with like a large grouping of atoms. We call it a mole, if you haven't heard that one before. And so this is an average number right here, and we refer to that as the atomic weight or the atomic mass. These numbers right here are guaranteed to be whole numbers. Guaranteed to be whole numbers. Because if you're talking about the mass of one atom, it can't be halfway in between. Right? You can't have half a proton, at least until we talk about quarks. But when you're doing the atomic weight or the atomic mass, these will be the ones that are like 12.01 or 14.01 or, sorry, that didn't work very nicely. Or what's another one? 36.45 or something like that, right? So then when we talk about atoms and ions, I've got some slides discussing those as well here. This slide right here probably is a good way of describing atoms versus ions. Once we understand the concept of protons being fixed, protons defines who you are, but neutrons can change. You can have any number of neutrons. The question is, how many electrons do you have? If something is considered an atom, it is neutral. Atoms are neutral. See how this guy right here has 9 protons, but it also has 9 electrons? That is considered to be neutral. This is called an atom. They have equal number of electrons to protons. However, most things don't stay in their atomic form. Normally they form what we call ions. And ions are where you change the number of electrons. Because remember how electrons are no longer like found inside the model, but electrons are outside of the atom, like they are in those energy clouds? Electrons have the ability to move, and so you can either gain electrons or lose electrons and form an ion. And you usually write those then with like this little charge in the corner, like say Na plus, or Cl minus, or O2 minus, or Ca2 plus. These charges in the corner then tell you how many electrons you've either gained or lost. Chlorine minus has gained 1 electron, because it's got a minus in the corner, right? O2 minus has gained 2 electrons. What about sodium positive? Did it gain a proton? Why can't it gain a proton? Okay, but why can't it have a charge of +1 because it gained protons, though? Why is proton gaining not allowed? Why is that against the rules? Because it would change the element. Remember, you are defined based on your protons, right? So if sodium gained another proton, yeah, you might want to call it sodium plus, but you'd never call it sodium plus. You'd call it magnesium, because magnesium is who actually has more protons. So in order to become positive, you actually have to lose electrons to become positive, and if you're negative, it's because you've gained electrons. Okay, so that's basically like a few-minute crash course in chemistry. A lot of you guys have heard this before? Okay. Let's get then to where physics matters then. So if we're continuing our history story, we're coming up into about the 1930s, and some of the context in the 1930s is that Hitler had started to become very aggressive in Europe. You guys talk about this in social studies at all? One of the things that I love about physics is that it truly overlaps with so many different disciplines. It overlaps with chemistry, it overlaps with math for sure, and a lot of the history is social studies. So 1930s, Hitler rises to power. The Third Reich begins in Germany, and there becomes a bit of a scientific breakthrough where scientists realized that there was atomic energy. Atomic energy. In the atoms themselves, we could actually harness energy there. And Albert Einstein was actually a Jew living in Germany, and he actually ended up getting out of Germany, fortunately, and moved to the United States. And in the late 1930s, early 1940s, the United States developed what was called the Manhattan Project. Heard about this? Manhattan Project involved scientists like Enrico Fermi, Robert Oppenheimer, Richard Feynman, Albert Einstein, and they were basically trying to make the world's first atomic bomb. And there was a bit of a race to this, because German scientists, who I don't know their names because they didn't finish first, but German scientists were also trying to make the first atomic bomb. And the Manhattan Project was ultimately successful in the year 1945? You guys know the context? What happened in 1945? How did it end World War II, though? Where? Hiroshima and what was it, Nagasaki, Japan? Right? And so the historical context is Germany ultimately surrendered in World War II due to a lot of other reasons, but Japan had joined the war, and Japan was not planning on backing down. And so in one of the most aggressive moves in probably human history, the United States decided not to drop just one bomb, but drop 2 atomic bombs. And it devastated those towns. Like, it wiped everything out. Radiation, basically, if for some reason you weren't killed by the bomb explosion itself, radiation was still lingering decades afterwards. And shortly afterwards, obviously, Japan surrendered. There's a lot of political questions as to whether or not the United States really needed to drop both bombs, let alone one bomb. Although I've read some stats that suggested that it shortened the war by a lot because of the fact that like it kind of they had a trump card, so to speak, right? They said we have a nuclear bomb, you don't, give up. Does that make sense? That's basically what we're going to finish today's lesson with. Then is that we're living with the realities of those scientific discoveries to this day, and many of the members of the Manhattan Project, they regretted their work very much so. They wished that they could go back and undo it. Because although, yeah, maybe it was good because it stopped the war, and really that's what they were focused on, right? There was a war, everyone's contributing to the war effort. Historically, now we live in a world where there are nuclear stocks built up. You know, the Cold War was basically a munitions race where Russia, although they were called the USSR at the time, Russia and the States, they kept building up missiles. Even to this day, Donald Trump is trying to the best of his ability, trying to keep North Korea from getting nuclear capabilities. You guys hear about this in the news at all, where North Korea is trying to do another bomb test and it doesn't work? Right. During the Obama administration, there were questions about, I think it was Iran, trying to obtain nuclear weapons and whether or not they would use them, you know, for nefarious purposes or not. So yeah, there's a lot of social studies impact based on where we're going to go from here. So let me get back to physics now because I went on a bit of a side rant. Once physicists and chemists realized there were these subatomic particles, they had to try a way to quantify and count them. Because it's really, really tedious to count 1 proton, 2 proton, 3 proton, and weigh them out one at a time. So they came up with a new unit. It was called an atomic mass unit, or we use the letter U for it. And you can read my notes on here. We don't actually use like kilograms a whole lot. You guys know how we've measured the mass of the electron to be 9.11 e minus 31. You know how we've calculated the mass of the electron, proton, and neutron? What physicists decided it was better to do is come up with a new unit called these U values, just because measuring kilograms is kind of ridiculous. And this actually explains a little bit about a periodic table as well. They decided to make a U value based on carbon-12. They just had to pick something to be the reference, and so a carbon-12 isotope is the definition. They decided that in carbon-12, what would be in a carbon-12 atom, by the way? Carbon is number 6, so it would have 6 protons. And it would also have 6 neutrons. Why would it have 6 neutrons? 6 plus 6 equals 12. And how many electrons would it have? 6. Why does it have 6 electrons? Because it was an atom. So, I mean, maybe a little ominous picking the number 666, but I think the idea was it was a nice round number for everything. There was 6 of everything in carbon-12. So they decided to make basically carbon-12 equal to 12 U's, which means that each U of it is a 12th of the mass of carbon. And this gets confusing because what we're really doing is we're breaking carbon up into 12 chunks. Even though technically there's 6 of these, 6 of these, and 6 of these, there's 18 subatomic pieces there. What they suggested is let's just break it into like round intervals. So carbon-12 basically gets to have 12 pieces. And they actually calculated what the average, this would be an average unit of mass. The average unit would be 1.66 times 10 to the minus 27 kilograms. This is on your data sheet. What is that number almost the exact same as? Not the charge, the mass of a proton. Can you guys find your formula sheets for physics? Not the one I just gave you, but your other one. Can you look up the masses of all the subatomic particles? So Zainab, you've got yours there. Can you tell me what's the mass of a proton? Okay, so 1.67 e minus 27. What's the mass of a neutron? Same thing? Okay, so the mass of a neutron is the same thing. And then the mass of the electron is 9.11. 9.11 e minus 31. Is everybody able to find those values for proton, neutron, electron? So at first this is going to seem ridiculously stupid, so you got to bear with me here. But they basically said, well, why don't we make the average atom inside of, like the average subatomic particle is 1.66 e minus 27. Why is this just slightly different than the mass of the protons and the neutrons? Anybody know? Why is this 1.67 and this 1.66? Because the electrons are so light. Yeah. So when you kind of average the typical particle, right, your protons and neutrons are 1.67, but these guys, the electrons, sorry, that's an E here. The electrons are so light that the average mass unit ends up being this. Okay? And this is a common way that physicists will then use to keep track of particles. This is a slide out of your textbook. Okay? And I don't use textbooks a lot, but once in a while we're going to reference these numbers here. On any test question or diploma question, they will have to give you these values. So don't worry about memorizing these, but maybe put a star next to these slides right here, because on future questions that we answer today, we're going to be coming back to these numbers. So for example, let's look at a couple of them here. Carbon-12, by definition, has exactly 12 units in it. That's how we defined it. Well, that means that an average hydrogen weighs 1.008. Or the average silicon weighs 29.973. Now that's not kilograms, that's like how many parts there are compared to what carbon has. We're going to use these masses right here when we do calculations. Now a person might ask, Chris, on my periodic table, there's those atomic numbers, those atomic masses that look like this, 14.01, 12.01, 1.01. The numbers in the chart look really close to those. Why can't I just use the molar mass? Why can't you just use the molar mass? Right. The reason why you can't use the molar mass is an average of many, many, many atoms. And we have to talk about the mass of literally just one atom at a time. Okay? So even though these numbers right here may look really, really, really similar to molar masses you might have done in chemistry, keep in mind there's a slight difference here. Those molar masses are the average weight of many, many, many different isotopes put together, and this is very specifically what unique isotopes are. And these have been weighed out very, very precisely. Like you'll notice that these go to 6 decimal places. We're going to need that in future questions. So I'm going to pause here for a second and then come back to history for a little while. I'm sorry, it's kind of the way this gets taught, I think. Again, we're back at the turn of the century, and scientists are trying to figure out this nucleus idea. So again, in the nucleus, what's in the nucleus? Well, you have a whole bunch of positives in a nucleus. You even have some neutrons. I'll go with zeros for those. And then around the nucleus, you have electrons. And there was a really fundamental problem that scientists are trying to figure out, which is, why does a nucleus stay together? Why does a nucleus stay together? What would positives want to do next to each other? They would want to repel each other, right? All of these positives right here, they have no desire to be next to each other. They're going to want to basically repel each other as much as possible, which leads to the question, why does a nucleus not just explode? Why does all matter as we know it not just randomly just explode into pieces? Right? So there was a theory. This is not true. We're going to prove why in a second here. But there was a theory. They thought, well, maybe there's some gravitational force. Maybe all of these protons next to each other, maybe gravity is causing them to become stuck together. So they thought maybe the gravitational force is stronger than the electrostatic force wanting them to move. I'm going to prove real quickly, though, why that isn't true. In terms of values, this formula right here is the formula for gravity. Okay? And I'm just going to make up some numbers. Capital G, if you guys remember, was 6.67. E minus 11. What are the masses going to be in the nucleus? Well, what's the things in the nucleus that are trying to repel each other or attract each other? Protons. Yeah, so let's go with the proton's mass. Now, let's not use the U value just yet. I'm going to come back to that. But let's use 1.67 E minus 27. And I'm going to square it because there's going to be 2 of them trying to attract each other via gravity. And then I have to divide by R. The problem is I don't actually know how close they are, so I'm just going to make up a random number for R. I'm going to use the number 1. I know they're not 1 meter away, but I'm going to show you in a second why it doesn't really matter what I use for that value. Because now I'm going to try to compare that to the electrostatic force. I'll use a new color here. In the electrostatic force, the K value we learned was 8.99 e to the 9. And then the Q values, well, what are the charges on those things? Perfect. And then we'll square it because we need two of them. It's a 19. Now, I still don't know the radius, but I mean, if I went with the radius of 1 right here, I mean, I should just keep the same number, right? So effectively what I'm doing is I'm saying the radius doesn't really matter because it's really in both equations. So if some of you have a calculator nearby, can you calculate what this value right here is based on gravitational force and compare it to this value right here compared to electrostatic force? So I'll do the same thing, but you guys try it real quick. I think I'm going to have to sit somewhere differently. My whiteboard is not writing very well when I'm sitting there, so I'm going to come join you guys here. 6.67 e minus 11 times 1.67 e minus 27 squared. So for my left-hand side over here, I calculated a value of 1.86 e minus 64. Anybody else get that? Perfect. Okay. And then for the other side, is that the one you're showing me? Perfect. Okay, I'm just going to steal Will's. It's 2.3 e minus 28. Now, the question was, is gravity going to somehow be larger than electrostatics? Is this number larger than this number? It's not even remotely close. I know the number is bigger, right? 64 is bigger than 28, but it's minus 64 and minus 28. So that basically debunked that theory almost immediately, that doesn't explain how the nucleus stays together. So there was a new theory. Physicists called this force that binds the nucleus together, they call it a strong nuclear force. And they suggested there must be some sort of force keeping all those protons stuck together. Otherwise, they would just want to explode, basically. And it's actually one of what we call the 4 fundamental forces. We've already discussed gravity in physics 20, right? I know maybe I didn't teach you, but you guys have learned gravity. We've also discussed the electromagnetic force. Well, in lieu of a better name for it, they just called it the strong force, and suggested that it must be the force that causes protons to stick together. And so they figured that this is what must happen. The strong nuclear force must be stronger than the electrostatic force, which means that the strong nuclear force is actually the strongest of all the ones that we know about, because we know gravity is actually pretty weak. Electrostatic is better, but the strong nuclear force is actually really strong. And physicists realized that there must be energy then stuck in the nucleus of atoms, keeping those atoms, like the protons, stuck together. If they could find a way to get that energy out of the nucleus, well, we could make nuclear bombs, essentially. So here's the word we use. We call it a binding energy. It's the energy which is like the glue. That's actually an analogy I use a lot. It's like there's glue that keeps all of these protons all stuck together. Here's basically the idea. And for those of you guys who are doing Chem 30, you'll recognize this diagram. There is some energy in the nucleus, a certain amount of energy. And if we can find a way to break the nucleus's bonds, we can actually release energy, almost like an exothermic energy diagram. Who's doing chemistry? Who's done this before? Some of you guys here? So I'm sorry, this doesn't actually work for everybody if you haven't done chemistry, but you'll see the analogy here is that there is energy in those bonds, and through an exothermic release process, if you've done like delta H in chemistry, we can get that energy out. So we're going to try an example now. And I'm just going to hop right into just basically doing the math for this. And we'll just calculate how much energy there is. What we've calculated on one of the previous slides is that a zirconium-93 atom has this much mass to it. So we weighed it on a scale very precisely, and we've weighed it out to 92.90647 atomic mass units. Now, that's actually a little bit off of what the items are individually. And so the concept is called a mass defect. Collectively, the zirconium weighs a certain amount. But if we were to weigh things out individually, these two numbers would actually not be the same as each other. And I'm going to prove that to you in a second here. So first, let's figure out zirconium in terms of collectively how much it weighs. It says we have 92.906 U's. How much did a U value average out to, though? 1.66 times 10 to the minus 27. That's how much a single U value was in kilograms. So I'm going to do a quick calculation and tell you how much collectively the nucleus weighs. 92.90647. I'm going to times by that 1.66 E minus 27 number and get this value. And I'm actually going to save like every sig dig I can just to prove this here. I got 1.5422.474 E minus 25 kilograms. However, what is a zirconium nucleus made of if it's zirconium-93? Go to your periodic table. Find me where zirconium is. What number is it? Okay, but that's its atomic mass, so we don't care about that at all. Yep, that's a distractor. Don't use that. What atomic number is zirconium? Number 40. You guys find that on your table there? Zirconium is number 40. What does that mean it's made out of? Well, it means it has 40 protons, and each of those protons is supposed to weigh 1.67 times 10 to the minus, 27. And it's supposed to have, how many left over? 53 neutrons. And the 53 neutrons are also supposed to weigh 1.67 times 10 to the minus 27. So what I want to do is I want to calculate how much individually the pieces are made of, and you're actually going to discover it's not going to be this number. Effectively, since protons and neutrons weigh basically the same amount, you have 93 pieces times by 1.67 times 10 to the minus 27. I got this number here, 1.5531 E minus 25. So I want to pause for a second to make sure everybody understands what I did here. On the left-hand side, I just literally looked up how much a zirconium atom weighs, and I converted it into kilograms. And then over here, I recognize that I have basically 93 individual bricks or Lego pieces. And if I add them all up individually, I get this amount here. Can you guys see that these two numbers are not the same as each other? So here's where the logic came from. There must be a mass defect. According to Einstein's famous equation, E equals mc squared. See how there's a difference in mass between these two things here? That missing mass is what's allowing these things to collectively fit together. There is some mass that should be on the side of the equation, right? If I added a little bit of extra mass to this side over here, this side would equal this side right here. But that mass isn't behaving as mass. It's actually behaving instead as energy. Specifically, the energy keeping this proton and this proton and this proton and this proton and 40 of their friends, it's keeping them from literally escaping. So if you want to figure out how much energy there is, binding energy in one atom, all we have to do is this. Take these two masses that we calculated here and subtract them and throw them into Einstein's formula. So take the 1.5531 number, subtract 1.5422474. I've calculated, I'm running out of room here, so I need a new slide here. I've calculated a mass defect by subtracting. So just a little note here, you subtracted these. I calculated 1.085, etc., E minus 27 kilograms. That is the missing mass. But it's not missing at all. It's just not acting as mass, it's acting as energy. And you know what? That's confusing. Except for the fact that scientists had already been here with electrons, because electrons are both waves and particles. So when Einstein eventually suggested that mass could be energy, people were like, cool, things can be two things at the same time, whatever. So that missing mass is really energy. So use the formula E equals mc squared, plug this mass in here, times by the speed of light squared, and that is how much energy must be keeping your nucleus together. We're going to take a break in a second here, but physicists then realize that there is energy in all of these atoms. So I'll take that number times by 3 times 10 to the 8 squared. It means that I calculated 9.77, I'll call it, times 10 to the minus 11 joules of energy. Now, that doesn't seem like a lot. To the minus 11 joules? That's not a lot. But wait, that was in one atom. How often do we use one atom of something? Never. Often we use, say, a mole of something. Those of you guys who've done some chemistry, remember what a mole is? It's 6.02 times 10 to the 23 atoms in a mole. So if I were to take this number here for one atom, and if I were to use a mole's worth of it, well, now are we going to get some energy? Yeah. Now we're going to get a lot of energy. So anyways, though, to answer the question, though, this would have been where we'd have stopped, because it said to calculate the binding energy. So the mass defect, by the way, would have been this number here when you subtracted them. The nucleus would have been done twice, collectively and individually, and then the binding energy is when you throw it into Einstein's formula. Does that make sense to start here? Yeah. Subtract them. So you got to calculate the mass of the nucleus stuck together, then the mass of all of the pieces one at a time, and they won't equal each other. The reason why is that when you shove them together, there's missing mass. That mass is actually in the form of energy, keeping them stuck together, right? Let me show this one more time. This number here is effectively the number 155, 154. This is the number 155. Clearly, this side right here needs some extra mass, but it's not in the form of mass. It's actually in the form of energy, keeping collectively all of these individual protons from exploding. So why don't we take a quick break here, because I know this is a long lesson. I know I've got another half hour or so. Can you guys come back in like, say, 2 or 3 minutes, and I'll continue here?
Why is the collective way less than the individual? Like, because there's energy between them.
Yeah.
Maybe weighs 48 pounds, Carson weighs 29 pounds.
Yeah.
And the energy would make them 100.
Yeah.
But the individuals, I would say, would be smaller than.
I know, it seems backwards, doesn't it? But the rationale is that, I'll go back to the slide here. All right, let me try drawing. I drew this out last night because I knew this question was going to happen. Let's say that you have together, you weigh 4.
Yeah.
But individually, somehow you weigh 5. That doesn't make sense, right? But the reason why is that there was hidden mass here that we didn't know about. We didn't know there was mass there because there was glue keeping them together. And that glue weighed 1. 1 plus 4 did equal 5. But we weren't weighing this as glue, as a mass. We were weighing it as an energy. Because doesn't it make sense that you need energy to keep them together?
Yeah.
So the mass truly was conserved. It's just we weren't observing it as mass. We were observing it as in its energy format.
So with the individuals.
So what ends up happening basically is if you could in theory separate them into different pieces, the individuals would now weigh more, because that mass that was keeping them together would then convert back into, from energy, it would convert from energy back to mass, and they'd each get a little share of it. Does that make sense?
Yeah, they get a little share.
Yeah, right? So that missing glue that was right here keeping it together, some of it goes to that one, some of it goes to that one, some of it goes to that one. So individually they actually weigh a little bit more, which is really goofy, like it seems odd. But once scientists were able to realize this, they realized that there is a huge potential of energy stuck inside the nucleus of atoms.
So like a string that weighs 1 pound that's together, they cut it.
That's a good way of putting it. Yeah. So I was going to bring in Lego blocks, right? Imagine that my daughter makes a toy out of Lego, right? And so I weigh all of the blocks individually, right? And they weigh 5. But like, they weigh 4 together, which seems weird, but the reason why is that maybe I put some glue on them, right? But I didn't account for the glue when I was weighing them, right? So this scale doesn't weigh glue. But when I take them all apart again, the glue that's on them, now it's counting as mass again, right? So, yeah. Weird, hey? Yeah, very weird. Oh, goodness, I still have lots to get through. Okay. We got this. For those of you guys who are in here, whenever you get back, can you guys try the example on the next page? I've done one for you. Can you guys try the one for finding mass defect and binding energy for magnesium 24? If you're looking for the number that you need, it's on this slide back here. Magnesium 24 is on this slide over here. It's at 23.985042. 23.985. Where is it? 985042. Okay, so for those of you guys coming back here, I've looked up the mass number for a magnesium nucleus on that table a few slides back. This is the mass of magnesium based on the table. Can you guys try to calculate the collective mass, which is right here, convert it into kilograms, then individually count out 24 protons and neutrons, find that mass, subtract the 2, that's your mass defect, throw it into E equals mc squared, that's your binding energy. Give that a try, see that you can do that. I'll give you a few seconds head start here. Where'd that calculator go? Here it is. Okay, so let's do it individually first. How many pieces does the magnesium 24 have in its nucleus? Yeah, 24. Because literally that's what the number 24 is for, right? Because the 24 tells you how many protons and neutrons you have. But protons and neutrons basically weigh the same thing. Right? So individually you have 24 pieces, and they each weigh 1.67 times 10 to the minus 27. We're going to do that in a second. That's going to be the second half of this. So let's start individually. Individually, and then collectively in a second here, Malik, what you're going to do is you're going to take this number right here, and you're going to turn it into, convert it to kilograms. And that's where you're going to use the number 1.66 times 10 to the minus 27, and that's how many kilograms are in a U value. Yeah, so we're going to take this one and multiply by this to tell how much collective mass it has, and this is how much it should have individually. And these two numbers are not going to equal each other. Yeah, because they'll now finally both be in kilograms. Yeah. This number right here, because this is the number that I got off of a table. So if I go back a few slides here, this table back here, I know you can't see it all that well, but it says magnesium 24. It has been very precisely determined that this is exactly how heavy a magnesium 24, a single atom of it is, not a weighted amount, right? So that's where I got the 23.985042. That is not on your data sheet, so if they give you a question like this in the diploma, they would have to tell you this number. Have to tell you this number. So I guess why don't I walk you guys through this if you haven't already been trying this. There's 24 particles in a magnesium 24, right? Because it's number 24, right? So each of them weighs the same amount, protons and neutrons. So if I go 25 times 1.67 to the minus 27. Oh goodness, come on, Chris, you can do this. I have a total mass individually of 4.008 E minus 26 kilograms. And that is, if you counted them up one piece at a time, this is how heavy they're supposed to be. However, if we take the value in our data booklet that's given to us and times it by an atomic mass unit, which is just slightly less, so 23.985042, and I times that by 1.66, E minus 27, I end up getting 3.9815 or so, E minus 26 kilograms. I should have brought this in. Imagine that I have to bring in like my daughter's Lego. If I were to weigh all of the little pieces one at a time, they weighed this much. If I were to then build the Lego together and put that on the scale, somehow it weighed less. And that is so perplexing. How in the world can it weigh less when they're together than when they are individually? There is missing mass. It's not acting as mass anymore. Is it clear that there should be mass on this side right here? Like, to make these two equations equal to each other, there should be mass on this side right here. But it's not behaving as mass anymore. It's now behaving as energy. And that energy is what is keeping, collectively, all those nucleons together. Otherwise, they'd explode. So, if I ask you to find the mass defect, all you have to do is then subtract these two numbers. It's actually pretty easy to do. So, go back up, take this number, and subtract this one. I have calculated that I am missing, so I'll label this as MD, my mass defect. I am missing about 2.64 E minus 28 kilograms. That is how much is missing. But if I want to calculate my binding energy, I just have to go mc squared times that mass by the speed of light squared. This is actually something that really confuses kids. They think that the mass itself is there, but like that mass is the missing mass, right? So when you use the formula E equals mc squared, don't use the mass of the items. Use the mass that has been converted and is missing. Use that mass, right? So take the missing mass, times it by the speed of light, square it, and I calculated this value here. Sorry that I'm running out of room. I've got, I'll try to write neatly. I've got 2.38 E minus 11, and that would be joules. So that means that there is a little bit of energy keeping that nucleus together. Again, one nucleus, that's a tiny amount of energy. But if you had a mole's worth of this, now we're starting to get somewhere. Right? So that's going to lead to kind of our next topic. But I want to make sure everybody's good on binding energy before I move on. Does that make sense how to solve it? It's actually super easy. Calculate it individually, calculate it collectively, subtract the two, E equals mc squared. All of these numbers will have to be given to you in a table if you do this. Okay? Like this number right here, this 23.985 number here, that has to be told to you. Okay. However, this number right here is on your data sheet, and this number right here is on your data sheet as well. Okay, I'm gonna sit back here so I can face you guys again. The last side of like my lesson here then kind of gets to the point of, well, how were scientists able to actually create a bomb? And we're getting there. So the next thing we want to talk about is radioactive decay. The idea that materials have the ability to give off energy, radioactive energy. What's that? Okay. There are three types of radiation. They're called alpha, beta, and gamma. And we've already discussed alpha particles a bit already. In all of these cases right here, what's really happening is the nucleus of the atom is changing. For the most part, up until grade 12, when we talk about matter, we kind of suggest that, like, if you have gold, oh goodness, I can't write it all today. If you have gold cannot turn into lead. Okay? But that's actually not true. It actually is possible to have radioactive materials change their identity and change their protons and neutrons and electrons. And if they do that, it forms what's known as a nuclear reaction. The word we sometimes use is called transmutation. So So let me show you a couple of typical examples of this. The first one's called alpha decay. Imagine that you have a nucleus, and the nucleus is so jammed packed of particles that it kind of needs to get rid of a couple. Okay. What ends up happening is something called alpha radiation, alpha decay, where an alpha particle gets kicked off. It has 2 protons and 2 nucleuses. Sorry, 2 protons and 2 neutrons. Okay. It's helium. And what ends up happening is it kicks out a little particle, and the vocabulary we use is called a parent nucleus and a daughter nucleus. The parent is what we started off as, and the daughter is what it turns into. And this is basically how alpha particles are given off. The good news is though, that alpha particles are not dangerous at all. If you want to stop an alpha particle, paper will actually stop an alpha particle. So we don't really worry too much about alpha radiation. Let's try an example. Let's say that I gave you iridium-168. This is a radioactive material. How would iridium decay if it underwent alpha particles? So here's how you may want to try doing this. Iridium is IR, and you need your periodic table thing I just gave you. Can you guys find iridium on your table here? You need to know what number it is. Iridium's number 77. So if iridium is number 77, then it has 77 protons. And I would put the number 168 up here in the top corner, because that's how many total particles it has. Now, you don't ever do this in chemistry when you write a chemical equation, but our chemical equation today is going to involve iridium turning into something new. It's no longer going to be iridium. Now, if it's going to undergo alpha decay, it means it has to lose 2 protons and 2 neutrons. What happens if it loses 2 protons? Well, the bottom number is now 75, because there's now 2 protons less. Who is it if it's number 75? 75 is now rhenium. Never used that in my life. 75 is now Re. What's the top number going to be? Someone said 166. It's 164. Why 164? It lost 2 neutrons and 2 protons. Right? An alpha particle is 2 protons and 2 neutrons. So it means it's losing 4 nucleons total. So the top number goes down by 4. Remember, the top number is everything, protons and neutrons. So you're going to lose 4 particles total, but specifically the protons, you're losing 2 of them. But you still have to write out an alpha particle. This is the symbol for an alpha particle, and there's a 4 and a 2 in it. Yeah. Yep. Yes, exactly. Yeah, that's basically what was happening. Is it was undergoing some sort of alpha decay, and that's how it was shooting out those alpha particles, and it was just doing it slowly over time. Yeah, eventually it runs out. We call that half-life, and that's actually going to be one of the last slides I get to here, is the idea of eventually it runs out. Yeah, good point. Let me come back to that thought, because that's a good, you're almost ahead of where I want to go, but that's good. One of the things I need you guys to be able to do then is be able to just do basic adding. This 77 is 75 plus 2. This 168 is 164 plus 4. That's all. Right? The law is called conservation of nucleons, where basically you can't lose subatomic particles. They have to add up here. We can actually then, when we undergo a nuclear reaction like this can release a huge amount of energy, and we're going to do that on the next slide here. Whenever you have your parent, it's then going to turn into an alpha particle and a daughter particle. And we can actually do conservation of mass and conservation of energy kind of collectively and figure out how much energy is given off. So let's do this example here. This is the classic example of what's called nuclear fission. We're going to take uranium and we're going to have it undergo alpha decay. And this is going to basically be what the Manhattan Project discovered how to use in a bomb. So first, let's write an equation. Uranium-238. It's U-238. What number goes in the bottom corner here? Well, what number is uranium? Perfect. What does uranium decay into when it loses off a 4 and a 2 in an alpha particle? We'll just do some basic math. 238 minus 4 must give you 234. And 92 minus 2 gives you 90. So who's number 90? Thorium. Here's what we're going to do now. It's almost like doing binding energy, but it's just slightly different. We are going to calculate, based on the masses in that table there, the energy that we had when we began and the energy that we had when we finished. And we're going to calculate how much difference in energy there actually happens to be. When we calculate that difference in energy, that's going to be lost energy. That's going to get converted, lost mass. Sorry, I'm using mass and energy interchangeably. We're going to calculate this guy's mass. We're going to calculate these guys' mass right here. And when we discover that, it's actually not going to weigh out to the exact amount we expect. Uranium-238. Let's go back to that table. Uranium-238 is right here. It weighs 238, 050,788. 238, 050,788. One more. 238, 050,788. Now I'm going to go look up thorium. How much does thorium have left when it's done? So thorium 90. Where is that? No. Thorium there. It was thorium 234 we did, right? 234, 043601. 234, 043601. I'm going to forget that. What was it? 244, 043. Someone find that sheet and just help me out here. What's thorium's number? Who has notes in front of them that can look it up for me? Yeah, but like what's the number off that other sheet there? 244, 043? 601. Okay. And then lastly, for our alpha particle, in order to calculate the mass of an alpha particle, we're going to need to do 4 times 1.67 E minus 27. Why am I doing that? Well, an alpha particle has 2 protons, 2 neutrons. A neutron and a proton basically weigh the same amount as each other. So what I'm going to do is I'm going to try to calculate the mass that we had before and the mass we had afterwards. And hopefully we're going to discover there's a bit of a difference. Only this number here I still have to convert. So I still have to times this by 1.66 E minus 27. I still have to convert this one as well. 1.66 E minus 27. So this number I found on the data sheet. This number I found on the data sheet. And an alpha particle, I just pieced it together because I know what it's supposed to be when it's done. Yeah. Depends on whether you're using an atomic number, like if you're using these numbers from back here, these ones right here, then you have to use the 1.66 number. Otherwise, if you're using a something else, you'll have to use the 67 number for protons and neutrons. Good question. Technically, we should actually be using these numbers right here. It's actually 1.672 and 1.674. We technically should use those numbers, but that's really tedious here. So let me go back here now, and we're going to try to calculate the mass that we had when we were uranium. We're going to try to find the mass that we have when we were thorium, and we're going to try to find the differences between them now. So, calculator time. $238.0507. Ooh, was that 88 times by 1.66 E minus 27. I've got a value here of 3.95 E 20 minus 25. So we started off with this much mass in our uranium. And then over here, I've got to kind of put these together. So I'll do the 244.043601 times 1.66 E minus 27. Right here? Oh, I screwed that up. Thank you. 234? Thank you. That would have made a huge difference. Okay, let me fix that. 234. Okay. And then I still need to add on 4 1.67s. So I have a grand total here of, I'm going to need more digits. This was 3.951,923 E minus 25. This guy over here, though, was 3.951,643. It's really close, isn't it? You got to be tedious with your work here, so hopefully you're able to follow along as to how I did all these numbers. But I've calculated an initial mass here and an initial mass here, and you'll notice that it is slightly different. This one goes 9516. This goes 9519. It looks like we've gained mass. But we didn't, because that mass was really in the form of energy. And so I'm not going to do this calculation to save time if I could. All you've got to do is subtract these two energy numbers, throw it to E equals mc squared, and that'll tell us how much energy is actually released. Again, it's a small amount, but it's only for one atom. Okay. So that's more or less the first part of my lesson today, is the idea of, in order to calculate E equals mc squared, calculate before and after amounts of mass. And when the before and after amount of mass is not equivalent to each other, subtract them, throw it into E equals mc squared, you've got your answer. Okay. It's annoying to write out, like it's really tedious for me to do all these numbers right here. But hopefully you can follow that. Let me finish off. I've got 10 minutes left here. I want to finish. Oh, you have a question though? Yeah, so I mean, it's this number minus that one. Yeah. You get the idea though, right? Subtract the two, big from small. And that's how much the missing mass was in the form of energy. There was more energy over here keeping the uranium together. Okay, let's talk about the remaining types of radiation. Another type of radiation is known as beta decay. And what ends up happening in this one right here is this strange process. A neutron converts into a proton and an electron. Think about that for a second here. Isn't a neutron neutral? And if you were to combine a proton and an electron back together, it actually adds up to a neutron. Look back way at this first slide here. I know it's a long lesson here, but look at this one here. Your proton was 1.672. Your neutron was 1.674. A neutron is slightly heavier than a proton. There are some theories that actually inside of a neutron is really just a proton and an electron shoved together. And they're neutral then. And so that extra mass is due to the electron shoved inside there. So it's actually possible then for neutrons to actually break into pieces, and they break into a proton and electron. Only we don't call it an electron, we call it a beta particle. And the symbol is right here. It's the letter B from the Greek alphabet for beta. It actually has a 0 on top and a -1 on the bottom. Let's explain that convention. The 0 on the top is because we believe that really it functionally has really no mass to it, this electron. The electron weighs nothing because it's not even part of the nucleus. But it's given a -1 because it's almost like it's subtracting a proton, right? You're actually losing a proton or losing a nucleon to make this occur. Beta particles are actually negative charges because they're electrons. So I want to show you some examples of this. I think this is the best way of describing it here. No, where's it? I don't have an example. Here it is. Here we go. What ends up happening is a neutron will actually form a proton. It'll form this beta particle, which is effectively an electron. And there's actually a third part that scientists eventually discovered. We're going to talk more about this in our last lesson. But they discovered something called an antineutrino, which was actually the remaining mass. They discovered that like something was missing. You guys can read my notes here, but they discovered that it actually traveled really slowly. And they couldn't figure out where the missing piece was. They realized the neutron made a proton. They realized it kicked out an electron. But like the electron was going so slow, they couldn't figure out what was missing until they eventually identified this antineutrino. And without trying to get into like too much detail, we're eventually going to talk about something called antimatter, which is really cool. Like everything has like its opposite doppelganger. So there's a neutrino and an antineutrino. And there is a electron and there is a positron. It's like it's opposite charge, same mass. So we're going to get to that in a little bit of a later lesson. But that's basically how beta decay works. It's actually also possible to have something called beta positive decay. And this is where it kicks out a positron. That's that antimatter idea as well. So a positron is effectively an electron that's positive. Somehow you have an electron with a negative charge, but it has the mass still of 9.11 e minus 31. And so we give it this symbol right here. It's still a B, rather than having a negative 1 charge, it has a positive 1 charge. And so this is how beta positive decay works. A proton turns into a neutron, and this positron, and it kicks out not an antineutrino, but a regular neutrino. And if you're starting to give me some funny looks here, that is normal, because this has all of a sudden got really weird, where it's like, what are these other particles? We're going to get to that. I've got a whole day dedicated to like the subatomic particles. But if you can basically recognize that beta decay involves kicking out electrons, that's important. So let's try an example here. Let's try to figure out the beta decay of thorium-234. And we're then going to try to figure out the released energy in mega electron volts. And I might have to pause here and just pick this up again tomorrow. So, beta decay of thorium-238. Well, thorium-234 looks like this. What number goes in the bottom corner? 90, because thorium is number 90. Now this is where beta decay gets very strange. It's going to kick out a beta particle, which is effectively an electron. So we're going to kick out an electron. The question now for us is, what goes here? Now what happens in beta decay? A neutron turns into an electron and a proton. So it actually means that we go up in protons. We actually get an extra proton back, which is really strange. Rather than your protons going down, your proton numbers goes up. But remember, a neutron, a neutral neutron, is creating a proton and an electron. This right here is your electron, but where does the proton stay? In the nucleus. So your bottom atomic number actually goes up by 1 to 91. What about your top number, though? What should happen to it? Actually, it's going to stay the same. Yeah, it'll still be 234. The reason why is that the top number counts out everything in the nucleus. You went from having a neutron to a proton, but you don't change the number, right? It just changed the format, but you still have the same number of items in the nucleus. It's just now there's an extra positive in there, and a minus got kicked out somehow. So number 91 then is number 91 is protactinium, so Pa. So since I'm really running out of time right now, why don't I end with this thought for you guys to try for homework? Can you guys try to calculate the amount of energy released? Now, let's not do mega electron volts. Let's leave that part for later. But do you guys think you can calculate how many joules of energy there is? You've got to find the mass of this, the mass of this, the mass of this, add them all up. They won't be the same. The missing mass will then turn into energy. Why don't I give that to you guys as like a homework task? Okay. Where are you going to find all these mass numbers? Back on this table, way back here, hopefully. Which ones did we need again? We needed thorium-234 and Pa-234. So hopefully they're on this chart right here. Thorium-234 is right here, and Pa-234 is on the chart right next to it. So use these numbers here, and why don't we leave that for tomorrow? Thanks, guys. This is a long lesson. I'm sorry. Really, these next 3 lessons, they kind of go just in one consolidated chunk. So as of Thursday, we're going to be done learning new curriculum. So I'll pick this up tomorrow, and then we'll continue into fusion and fission